So, hi, Jan. Usually you know me. Today I'm going to talk to you about rollups. What are rollups? Well, they're a layer 2-ish solution that we're going to talk about over the next 30 minutes or an hour, depending on how long this takes and how many questions you have. If at any point you do have a question, do let me know. Some disclaimers. First, spent a lot of time looking at these, but I'm probably still not 100% on everything. There's no standard text, and collecting data from multiple sources leaves some things to be wondered or clarified. Right? There's going to be some gaps in knowledge, and I'll try to avoid them as much as I can. If you ask clever questions, perhaps you will find them, in which case I won't have a good answer for you. But do ask. I would like to know what I don't know and what you don't know, and I'd like to fix both of those issues. So, without further ado, what are rollups? Well, at a glance, without defining them just yet, they're a layer 1.5 to 2 solution, depending on what you would call a layer 2 solution. Typical layer 2 solutions that you're probably familiar with include plasma and state channels, and we'll talk about those in passing during this talk. Plasma more so than state channels, and those are probably sort of the standard full-fledged layer 2 solutions. Rollup is kind of somewhere in the middle between a layer 1 solution, which is the Ethereum mainnet itself, and these other layer 2 solutions. It's going to be faster than the mainnet, the layer 1, but it may not be as fast as a layer 2 solution. On the other hand, what we will get is some things we really want much more quickly in terms of implementation and design. Although, I mean, it's still taking quite a while to get to where we are now with rollups. Turns out there was actually research going on this for years, and it's not all new stuff. But we will get things like speed up, maybe not as much as a full layer 2. But we'll also get really nice things like full smart contract support, which, if you looked at Plasma implementations for the most part, is entirely lacking. So Plasma does really good transfers very quickly, but most implementations, if not all implementations, fail to deliver full smart contract support, or at least fail to do so currently at their current stage of implementation. So maybe in 5 years or 2 years or some unforeseen amount of time, we'll get a nice Plasma going, but we don't have that yet. So people were looking at Plasma and they thought, oh, what about these other properties of speeding up? Can we trade off some aspects of Plasma and just support the things we really want instead, and maybe not get as fast? And so that's where rollups sort of came from, distilling the essence of these layer 2 solutions into something that's easy to implement, has full support for the tools we want now, and still better than layer 1, but still just as secure, which is also nice. In short, rollups are lazy Plasma. Plasma has weird things like exit games and data unavailability and things like this. The rollup design, as you'll see, or at least what I'll try to convey to you, is that it's Plasma without all these fancy tricks. Don't do exit games unless you need an exit game, right? And for Plasma, that was a nice, there were reasons for wanting that. For rollups, we'll see that this is not strictly necessary until it becomes necessary, in which case we'll deal with it. And lastly, we want to make things in rollups just as close to mainnet as possible in terms of support. So everybody said in terms of smart contract, but we want even more than that. Plasma, when the specs did enable smart contracts, did not necessarily enable the same tooling to be used. So if you had contracts aimed on a Plasma deployment, you had to take special care when you're writing those pieces of code to either not interact with the main chain when you shouldn't have, or to explicitly make your incentives clear to users, and to do a bunch of weird things. In short, you also didn't have tools. You had no tools. You had no EVM, right? Because you didn't have a Plasma chain simulator. You had an EVM chain simulator, and there was a gap there. The Plasma contracts were missing if you were a dApp designer. You didn't have those, and if you did have the source code, you didn't necessarily have them configured to run on your testnet, and your tooling was all out of whack. And so rollup, the optimism, at least based approach, tried to also correct this. And from what I gathered, they've done a fairly good job of this. About 80% they claim of tooling for the Ethereum mainnet should transfer instantaneously, or more or less instantaneously, to rollup contracts. So if this actually works, and they do have demos, and I'll talk about a demo briefly at the end, though I won't show one because I think you guys can all go have fun with it. Then we might actually see some rollup based contracts coming into the audit pipeline, which would be really nice for business, and just because it's a nice technology. It's also really cool because even if you don't know it, you actually know what a rollup is because it's just a blockchain. Because now it supports the full suite of Ethereum. You can sort of just consider it as another version of Ethereum, but it's running on the Ethereum mainnet, so it's blockchains and blockchains. And then if you do a rollup in a rollup or a plasma in a rollup, you have 3 layers of blockchains. You just have blockchains all the way down until you run out of recursion, and that's totally fine. Everything works out as long as you have full smart contract support, which in rollup you do. So why do we want this, or how did we get here, I suppose is the better question. So the history, getting to rollups. It's taken us a while to get here, but it's not new. As early as 2014, Vitalik comes along and suggests some layer 1.5-ish to layer 2 solution called a shadow chain. What is a shadow chain? Well, it's just a blockchain that runs parallel to your main net blockchain, and people produce blocks on it, and they occasionally commit blocks onto the main net, and then things happen. We'll talk about the details in 2 or 3 slides. Sometime later, 3 years later, I think, 4 years later, in 2018, I can see, Vitalik comes back and says, hey, ZK Starks and Snarks have come a long way. Shadow chains kind of sucked, but look, we can do a bunch of things with ZK Snarks that sort of capture the essence of what a shadow chain should have done in the first place, using this fancy, cool ZK Snark technology. And look, here you go, 500 transactions a second. Boom. This implementation, I don't know if this was ever actually implemented in practice. I didn't look explicitly for any of these, but these came to be known as ZK rollups, zero knowledge rollups, because effectively that's what they were doing. They were taking some information and rolling it up into a single transaction and using ZK knowledge to make sure it's all correct. And if you're still unclear what a rollup is, it's fine. I haven't defined it. We will get there, I promise. And then recently, July last year, Ethereum optimism sort of comes along. I guess that was technically this year in terms of the Optimism brand starting in 2020, in January 2020 this year. But the group Optimism used to be Ethereum Plasma, and they developed this nice system called the OVM, or the UVM, because it's technically EVM, and they put out accents on top of the O. And I think at this point, they must have started to realize, oh, Plasma is hard, and really what we care about is just these other nice properties. And the OVM was their first explicit, I think, introduction of an optimistic rollup, which is, again, yet to be defined. But they cut all the hard part of Plasma. I don't think they had stopped officially working on Plasma spec at this point, but they said, hey, let's just distill it to what really matters. So whatever the OVM is, and we'll get there, becomes effectively optimistic rollups. And they may not have been the first, and they're certainly not the last. There are several projects working on this type of technology, as we said. Sort of in parallel to all of that, right? Maybe not always at the same time, not always at the same vigor or rigor. Plasma was being developed in 2017. So when I started to join the company, Plasma was just being written, and oh boy, was that a nice idea. Talked about it a few times now. I have several talks on it. If you have more questions, do let me know. But Plasma, nice idea. And if you've read that paper in the top left corner of the slide, underspecified that, it was this nice pipe dream, and they had never really put pen to paper before writing that paper. In terms of code, I guess that's bad phrasing. They obviously put pen to paper to write the paper, but they never sat down with a compiler and started to write what a Plasma contract should look like. It turned out to be really hard. They swept a lot of things under the rug, which opened up the floodgates to research on Plasma. And Plasma gained a lot of traction from a lot of different research groups. We've certainly looked at these projects ourselves. But it had a lot of problems that need to be solved. Eventually, some of these were solved. The first version sort of came out as minimal viable Plasma, aka MVP. It was the first one to actually be able to kind of work. From that, we forked into a bunch of different things. We had Plasma Cash, which did away with the 2 signature transactions, so it improved the UX a little bit. At possible cost or change of making tokens not fungible. Or you had, just strict improvements, which are just more viable Plasma, for example. And that's just increasing the simplicity of the system, making exit games that work better, formally looking at what it means to have a finalized state for your Plasma chain, and how to support slightly more general actions. You don't strictly have full smart contracts, but you can do more than just sending money back and forth, which is what, say, Plasma Cash really excelled at. I don't think anyone doubts that Plasma Cash is really great for that use case, but it's only one use case on Ethereum, and we want to be able to do more than that. Ethereum is a decentralized computer, right? It's supposed to be able to do more. So in the last 3 years, Plasma has also been seeing a lot of work. And at some point, people realize, oh, this is getting out of hand, right? This is what happened to the Plasma space. This is a map from maybe late last year, and oh boy, there's a bunch of different Plasma projects up there. And if you look, only the stuff at the top right really support general computations. Not always completed. I don't know if there's a Plasma Leap implementation. I don't think there is. Not one that's fully functional. Other things, with zero knowledge proofs, which might improve it. Maybe the connection's unclear. Also start to fork off because we start seeing this connection of these two technologies between Plasma and zero knowledge in a way that I haven't described in any of my talks, but we will sort of touch on during this talk. And then we see a bunch of other things, right? Just general efficiencies, or changing from accounts to tokens, or different types of models for just keeping track of whatever limited state the Plasma is supposed to be. And I, among others, probably thought that there was too much going on here. In fact, a while back I proposed doing some research on just distilling the essence of what Plasma is. And people must have been thinking along the same way, because as this kept happening, people kept trying to make it simpler and simpler. And I think what came out of it was rollups. So still putting off what a rollup is because it is sort of technical. And I think the best way to get there is to build up through these iterations that we've sort of just gone over. In particular, the 3 iterations on the second slide here, third slide, which is to go from shadow chains, what a shadow chain is, to a ZK rollup, and then to the optimistic rollups, which are now gaining traction and popularity. So to put them all back in context, though, what we're going to be talking about is stuff in the orange. Right? We're going to talk about optimistic rollups and ZK rollups in depth, and it sort of assumes a little bit about the other layer 2 solutions, Plasma and state channels. We won't talk about state channels almost at all, but we do want to compare them because we want to know why we're doing ZK rollups if state channels exist, right? If state channels exist and they're useful, don't reinvent the wheel. Well, state channels have some flaws, not surprising. For one, you can't do arbitrary users in state channels. So for a state channel to exist, you must have everyone who's ever going to be using that state channel to be present at the time it's created. So that's a big problem. That's one of the reasons why it's not particularly useful. Whereas Ethereum, you can have people join and leave the network at will, and there's no issues, right? So we'd like to mimic that behavior much more nicely. The problem, the benefits you get from having state channels like this, though, where you have restricted user base, is that you always have unanimous consent. Everyone always agrees exactly what's going on, because everyone who's in there, all their keys, if something's been signed, everything's very sort of nice. You always have unanimous information and agreements. It's great. If you don't, you just slash someone, you penalize someone. There's a way to do this. In fact, the way to do that is this bottom row. It's a liveness mechanism. And it's something that'll come up a little bit through this talk, but something that's really, really important, especially to make the leap from shadow chains to ZK rollups. Liveness mechanisms just mean that there must be some way for an arbitrary user to force their transaction to actually be included or processed somewhere, right? If someone sends me money and my block producer withholds all that transaction saying I get money, I'm going to be pretty upset. I want a way to force that money to come into my hands, right? So a liveness mechanism allows you to do this. In almost all cases, certainly in all cases that we're going to talk about today, that is just you go to the Ethereum mainnet, find the appropriate contract for the layer 2 solution you're using, and you say, hey, look, someone signed a transaction. I never saw it. Force this to be included. And the answer is typically, okay, we're going to include it, or someone's going to get slashed. In which case, you take your slash, and you're still probably pretty happy. Okay. So liveness mechanisms, pretty much the same across the board. This is very clear in state channels, especially if you're familiar with the Lightning Network. Someone promises to send you money. You don't get it. There's some way to recover the funds. State channels are also really, really good in generalized state for specific applications. There are people right here in Toronto that are working on things like state channels for tic-tac-toe or Battleship or other small games that will generalize to other places, right? People L4, I think they're doing state channels, or they were doing state channels. And it's really good if you have small deterministic state, and you can force these updates through liveness mechanism. If you're playing tic-tac-toe and your opponent stops playing because they know they're going to lose, you can force them to time out and take a bond or something like this. And they're particularly effective when the state is small. Right? Tic-tac-toe has only 9 squares. Not too hard to track on chain. You can store all that if you really need to, and you can process all of that on chain if you need to. And so you need some way to verify that, but if you can do that on chain, fine. And Plasma never really solved that problem. So the next 2 columns on the left, optimistic Plasma, and to a much more shady degree, ZK Plasma, because we're just not going to talk about ZK Plasma too much. Most people here probably are only familiar with the optimistic Plasma, which is to say everything goes well unless it doesn't, in which case you just challenge a fraud proof and then you're fine. Certainly the OMG Plasma variant is of the optimistic kind and not the succinct proof ZK Plasma kind. But Plasma has this other big issue, aside from the fact that you can't necessarily verify all state transitions all the time because they haven't really tried, and most people just do transactions of tokens or assets or very small state changes on Plasma. The bigger problem with Plasma is you have this sort of operator who is in charge of producing new blocks, so Plasma chain blocks, right? Something like this. Operators go by different names, aggregators, operators, Plasma node runner, something, bunch of names for these things. Someone has to put all these blocks together, and the assumption in Plasma for the most part is you have to kind of trust them. And most specs that we've seen so far say that if you don't trust them, specifically if you have explicit reason to not trust them, you bail, and everyone else on the chain has to bail as well, right? So you see an operator start forging transactions, you say, hey, it's time to leave, you have to exit or mass exit, which is even worse, slows down all the chains, real pain. It's a problem. But it was nice in theory because if Plasma works, correctly as this sort of envisioned, then you get a nice efficiency speed, right? Instead of watching everyone's money all the time for invalidity of transactions, you get to watch only your money all the time. You could probably fall asleep at the wheel, but never recommended. But at least you sort of only have to care about your money. And this more closely resembles the real world situation. I typically don't care what Alex does to his money, and if he tries to fake, some transaction, he gets caught, that's on him. I don't really care, right? Sorry, just calling out any arbitrary name I see. If he gets caught, he'll get penalized. That's fine. As long as it doesn't touch my money, I'm pretty happy with the outcome. Now, of course, there's real world issues there. If he's doing something in the stock market that will affect my money indirectly, I maybe care. But for the most part, I only check my bank account on a daily or weekly or monthly basis, right? I don't check Alex's. In fact, I typically can't. In Ethereum, though, we have to do this always checking everybody thing, right? I always have to make sure that every transaction is always valid from some account to some other valid account. So I know everyone's bank account all the time and have to make sure that every time anyone sends any money anywhere, it's a real pain, right? This is where a lot of the slow down comes from. And so in order to achieve this, watching your funds type property, you design a system where you don't necessarily give all people all information all the time, because, well, if you did that, why wouldn't you just build a new Ethereum layer 1, right? And so the Plasma design inherently captured that somewhere and said, hey, don't watch everyone's money all the time. That led to its own suite of problems, right? The data availability problem became rampant, and many iterations and exit games arose to try to solve this. Some were successful, some not so much. Pages and pages on ETH research, I'm sure you can find on this topic. And so maybe there's a middle ground. Maybe we can sort of necessarily have everyone's information all the time, but maybe I don't need to check everyone's information all the time. Or maybe I'm not really incentivized to check everyone's information all the time. Right? If I'm producing a block in Ethereum, I sort of have to do it because if I get the block reward, I need that block to be valid. But maybe there are cases where most blocks I don't care about, but if I wanted to, I could go and check them and make sure that they're invalid. And if they are invalid, I could get something back for them. And that's in a very, very dense nutshell on optimistic rollups. We're going to give everyone always all the information if you want to compute them, but we're not necessarily saying you have to, because if you wanted to, you can, and if you don't have to, right? So if you get your money, you're probably going to go on living your life. If you don't get your money, you can go back and look at the state and say, hey, I should have been getting some money here. What went wrong? And so this rollup captures that nice property where everything goes nice until it doesn't, and then you fix it. That's the optimistic. To get there, we will talk about ZK rollups instead, which is where nothing can really go wrong. There will be different downsides for that model. In particular, the use of ZKs, zero knowledge proofs, or Starks. That becomes a downside to some degree because ZKs are hard and you can't really do general state computations just yet. In theory, perhaps. In practice, probably not. So ZKs, nice, not a deal. Without further ado, let's build towards optimistic rollups. Step 1, shadow chains. What's a shadow chain? It's a blockchain. Boom, we're done. I mean, that's the oversimplified version of this. Shadow chain is literally just a chain that runs in parallel to a different chain. It shadows it to some degree. It's not shadowing all the data on it, so the shadow chain might be a bad name. But what actually happens is you have an Ethereum mainnet going along with a contract that says, here's my state root for my new shadow chain. Some people will come along, propose a block for your shadow chain. Some people will take those block headers, commit them onto the Ethereum main chain, and they won't be finalized for 2 weeks. Simple. If within 2 weeks of publishing a block header, or K blocks, for example, someone finds an error in that, revert the chain from that block forward, right? That's pretty straightforward. You can see this very easily in parallel, like by taking the Ethereum model, just say, if at some point you had a wrong one, just do a reorganization or a fork off of a different chain. Now you have the same problems though with all of your mainnet problems. Who's producing these blocks? Leader selection for your consensus. What does it mean to verify that something has gone wrong? That never really, was formalized. Who's getting the data for all of these blocks? Well, if I want to know something went wrong, I had to watch all the transactions all the time to make sure something was there, and I still don't necessarily have a liveness mechanism. I think you probably could force a liveness mechanism, but maybe you're already back into ZK rollups or optimistic rollups. So basically, 2 weeks, something goes wrong, you get to revert, and then it's fine. Also, really damaging if something does go wrong, you've lost possibly days and days of blocks, which is, not an ideal user experience to say the least, right? 2 weeks is a long time, and if someone doesn't find it until the 13th day in the 23rd hour, well, a lot of blocks got in on that fraudulent data, some of which may have been double spent by now, right? Especially if there's no exit game checks. And the initial spec didn't really talk about any of this. This is a nice post by Vitalik, but it's not so nice that it was fully spec'd out, and I wouldn't want to be the engineers trying to code this on day 0. Be a fun project, though, I guess. To see this again, this is an image just from Vitalik on his blog post. A lot of his material from these slides are not mine. Some of them are. This one is not. This is from Vitalik. I should include a source. What are the nice perks, though, of a shadow chain? If you did want to take this sort of risk of 2-week reversion on, which I think is one of the bigger issues, what do you get? Well, you get state transitions because your shadow chain can be any chain you want, right? You don't really care what that chain looks like. It can be Ethereum itself. You can make a fork of Ethereum, use the same code base, just call it Ethereum 2, not 2.0, but Ethereum 2 or Ethereum B, or pick your favorite name, right? And it has all of the same stuff, right? So you still need signatures to sign stuff, so you can't really do some fraudulent transactions of some nature, but you do get smart contracts. But you haven't solved the data requirement issue, right? You still need to have everyone watching everyone's money all the time. Admittedly, the size of transactions might be smaller because you only care about the people on your shadow chain. Because sort of once it hits the mainnet, like the mainnet transactions are obviously somewhat secure, but you still have to watch all the information coming through your shadow chain. It's kind of a pain. Okay.
Jan?
Yep.
Is it fair to say that shadow chains it's like an umbrella term that differ from side chains in that there's not sort of a separate node and shadow chains are appending on a smart contract?
I think you could probably, use shadow chains and side chains pretty interchangeably.
Got it.
I don't know that they would be. I don't know what the distinction would be if there is one. Yeah, basically you're still publishing commits and headers to your data on the mainline chain. As far as I know, this is what people called side chains back when I started looking into this like 2 or 3 years ago. So yeah, I'm using the shadow chains because that's what Vitalik uses, and I don't want to slip.
No, that's fair. I just wanted the clarification there. That makes sense. Okay, thank you.
Yeah, it's a good point. Side chains might be more familiar to people. Okay, but then you have the rest of the problems, right? Who runs this? Proof of work to produce blocks, pain, sharding, and proof of authority or proof of stake hasn't really been tested. This seems like a technology that doesn't seem like it's particularly well thought out. It seems useful. It seems like it has some nice ideas. Probably a lot of engineering bugs. I don't know how many people looked under the hood at this like they did in Plasma, which caused a bunch of research to happen. But I'm guessing someone did because this eventually evolved into what we know as zero-knowledge rollups. So ZK rollups are our first true rollup of the day. And this is going to try to reduce that data availability requirement while still having a liveness mechanism. And we're going to use ZKs and zero-knowledge proofs. Sometimes I call them ZKs. Some sort of zero-knowledge proof somewhere to make our life a little bit more simple. And what the simplicity here will gain from zero-knowledge proofs is the verification of data correctness. In particular, the idea behind a rollup is you talk to someone else who will build locks or state updates for some collection of state data, right? Might be a smart contract, might be someone's accounts. It's some collection of state that you want to be updated into some state prime. And you interact with them as much as you can. Obviously, you have to buy into the system and draw out of the system to the mainnet contracts if you're trying to do something like this. Then they aggregate it and they sign it, and then they just commit the header to the chain. That's sort of the end goal. And so what you're seeing on the main chain is significantly less data. At worst, you see all the indices of the data and the values of data changed per transaction, plus one extra state. So you're not like the state Merkle root itself being changed. And that's not bad because you sort of need the first two if you're going to do all the data anyways. And for the last state update, well, you need something to track your additional state in some way because otherwise why aren't you just doing smart contract? And so that's captured in sort of what the mainnet contract looks like. So you will have a mainnet contract for a ZK rollup, something somewhere on Ethereum if you're going to develop this, or on your other blockchain. None of this is Ethereum specific, although obviously it has been developed Ethereum in mind, at least with these resources. And the system contract has very little information. It has literally just the Merkle root of an address book and the Merkle root of a bunch of balances and nonce. So this is like 2 32-byte fields, very small amount of data. And when someone comes along and updates this, they're just going to replace the Merkle chain or the Merkle root header there with the new Merkle root. If you don't know what a Merkle root, please raise your hand now, and I'll explain that. Otherwise, I just realized I didn't put a slide on what a Merkle root is. Okay. My apologies if you don't know, if you're just too shy to ask, please follow up afterwards. But in the ZK rollup situation, someone's rolling up these transactions. It's pretty simple. We'll call that person the relayer. I don't know why it's not the roller. I did the name. I'm not sure if ZK rollups were named ZK rollups when the actors were named, so probably that explains it. But then you also have the people who are going to be doing the state updates who want to transact. Those are called transactors for the obvious reason of wanting to transact. So what can a transactor do? Well, they register, or they deposit and withdraw, or they send. So register just means, they say, I have some initial balance here. You deposit in for the first time. It's a special case of deposit. Otherwise, you deposit or withdraw, or you send money to other people, ideally within this ZK rollup, because that's where all the data is being tracked. Otherwise, it should technically be withdrawal. So 2 types of actors. Transactors will transact. Relayers will relay. What a surprise. And relay is just roll up. And so what we're going to do is just have transactors transact directly with this ZK rollup system, which isn't necessarily on-chain. In fact, if it's on-chain, it'll be slow, so you don't necessarily want to do that. you build another sidechain if you want, you build a website if you want, you build whatever you want as long as it produces Merkle roots that you can sign and produce ZK snarks with. It doesn't matter if it's another sidechain or not. And what that means is you get, potentially instant transaction finality because, you've trusted someone to send the transaction on your behalf. This is like a bank. A bank can do it instantly. Why can't you? Certainly, this is the goal. Fast speed up, right? Instant might not always be the case depending on your implementation, but certainly faster than 6 blocks is certainly feasible. And what happens is you have all these transactions existing in this ZK rollup mempool, whatever that looks like, website, whatever. And the relayer comes along, takes a bunch of them, combines them into a consistent state because every transaction has, I'm sending 7 ether from myself to Sebi or whatever, and my nonce for this transaction is N. So the combiner knows exactly how to combine these into a nice aggregate collection, a block. And they produce that block. And as they produce the block, they also produce a ZK snark, which, if you listen to my other talk, means that that's probably correct. They haven't possibly screwed up, or at least, it's incredibly, 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 incredibly unlikely for them to have screwed up, right? That the straight probabilities means basically 0 that they screwed up. And so as soon as they publish this block or the state header, you can just check the ZK snark. And you're convinced 100% of the time, boom, you have done your transaction, it's included. If you don't like it, then there has to be some liveness mechanism, which we won't go into because it's just some way of forcing this transaction to come into a block. And that's sort of the uninteresting part. Basically, you just had someone prove to you that they did all this aggregation on your behalf. And now what does it take for aggregation to really happen? I won't go over that. Actually, I won't go over that either because I'm a little slow. Yeah, so we're here. Transactions combined in the sequence, it's provably correct. And what does that mean? Well, that means depending on the block sizes of the current Ethereum mainnet and the current gas prices, you can do about 500 transactions a second for only about 650K gas, which I don't remember the number of US dollars in my head, but it's not that much. It's significantly faster than the Ethereum mainnet. That's for sure. 500 transactions a second is much higher. And even if you're paying, 20 to 100 or more dollars for this, the aggregator can be set up in such a way that they take a fee. So every time that you do a transaction, you also pay 0.0001 or something to the aggregator, and that offsets the cost of them paying the gas because they're the only one paying this gas on the mainnet. Right? So someone has to pay for it. The aggregator who's submitting obviously should be the one who does that, and they're going to be in it for money, so they're going to want some sort of payment from you. And so actually, in theory, it's really nice. The problem is the ZK snark part. The ZK snark, that's, if you saw the polynomials and mappings of the last 2 talks or 3 talks I did, oh, what a headache. Not even sure I remember every specific part of it. But what I do remember is that was a real pain to do that for a very simple transaction. And so trying to get state machines into a ZK snark, I'm sure there are people getting, high degrees and lots of grant money to solve that problem. Until they solve those problems, this becomes just basic Plasma. It's a little bit nicer than Plasma in a lot of ways because you don't need this sort of trusted Plasma chain operator. In fact, the ZK snarks means everything's correct. And because the clear text, sort of the clear balances are always also submitted with a new text header, you can, in principle, always have all the information synced up, right? You don't necessarily need to track it, but if you wanted to, you could sync an Ethereum full node, and every time there's an update to your ZK rollup system, that corresponding update, which was provably correct based on the data they're providing, which is being included on chain, is available on your Ethereum mainnet chain. And so what happens is, you don't have to care until you do have to care because you're using snarks. You actually never really have to care. But if you did want to care, or your accountant says, I need your transaction history for the last 2 years or whatever, you can go back and look at the Ethereum mainnet chain data and actually track all this. It will take you a while. That's the price you pay. Or you can do it as, you can monitor it. either get a monitoring service like one we have, or just check once a day to see if your account balance has changed, or track it yourself. This seems like a problem that's solved elsewhere. So before I go any further, any questions? I've covered a lot of material and talked a lot. Any questions?
How much gas does a regular transaction cost? Like just sending, if I sent you an ETH?
Within the ZK system, 0. You're not transacting with me.
Well, I guess I'm curious about comparing it to how much like the gas it costs to aggregate everything on ZK Rollups on mainnet compared to a normal transaction cost.
I see. Like what an actual baseline is of send. I think send is like 2,000 gas or something. If I were just on chain sending you just straight Ether in a smart contract, I think it's like 2,000 gas. I could be wrong. It's small. It's definitely less than like 50K. I think 50K would be a very, very loose upper bound. But this is for 500 transactions. And if you send it to me within the rollup system, whatever that means, and again, I'm abstracting away because it's implementation dependent, it will cost me only whatever the fee of the aggregator charges. So, if they charge 0.00001 of the Ether I'm sending you, then that's how much it'll cost. Any other questions? Okay, so this is how we built up to optimistic rollups and what's an optimistic rollup. This is what we came to talk about. And now hopefully you have some understanding of what a rollup is in some loose sense and why we need to be here. And now what are they? Well, optimistic rollups are effectively the same system as the ZK system without the ZK and with optimism. What a surprise. What is optimism? Optimism is jumping back to this idea that more or less the plasma we're familiar with uses, where everything is going right until it doesn't, and when it doesn't, we can just submit a fraud proof to say, hey, something didn't go right. And so this is also much more akin to the shadow chain or sidechain solution, where you assume everything's more or less fine. If something's not right, then you revert. The difference is here, we're going to be very much explicit about solving a lot of these problems the first time around. So we're not going to just say, oh, there's some way to revert, or here, there's some way to, check invalidity. We'll try to dive a little bit deeper into what that means and, how you could do that, because that's really hard. And the last thing we really care about, talk about at the beginning, is smart contracts. We want full smart contracts so we can put blockchains and blockchains and blockchains. Okay. So same idea, we have an Ethereum main chain. We have some smart contract on Ethereum main chain representing our optimistic rollup. This title is a bit misleading. We won't talk about the OBM for at least two or three more slides. Basically what happens, I'll come along with a transaction. I want to send a transaction to someone in the ZK rollup system, right? Maybe I join, register, and send all at the same time. That's fine. It's not state channels. It's not locked. I think I probably have to send to someone who's currently in the system though. But that's small caveat. So I'll go ahead and do a transaction. I'll send it to whatever the aggregator looks like. The aggregator is the same person as the relayer in the ZK language, using different language because, surprise, surprise, the specs don't match. And the aggregators will take this transaction, and possibly other transactions, and they'll produce a state update. So they'll literally just say, okay, in their books, beyond the balances went from 10 to 5, or something like this. And they'll compute a new Merkle root for this new state, and they'll track the change that took them from the previous Merkle root to this new Merkle root. And when they get sufficiently many state updates, they'll put these in a block, and they'll register the block on the rollup contract. In addition, they may log the data that sort of went into that block. So they may say, okay, here's the Merkle root of the state update, and here's the transitions that took us from the previous state update to the current state update. And these aggregators will just keep doing this. In fact, it's very simple. The first aggregator to aggregate wins. I don't know if that's redundant or unclear, but basically the first person to submit a valid or possibly invalid block header to this rollup contract basically extends this chain. Perfect. That's what we want to some degree.
Is the state update, this is specifically the shadow chain state update for the Merkle root, right? Okay.
Yep. But now it's a state update in full too. It doesn't necessarily have to be just a balance too. It can be a full state machine. I haven't really said that yet, but yes, right. It could be a variable changed, from true to false, which is, not much more conceptually difficult to envision than a balance going from 7 to 5 or something. So it's full state of whatever state changed. And we actually don't need to worry about the details for another slide or two. So the block will come and they'll produce it. And they'll say, here's the header, here it is, and the next person can just append a new block to that. And the catch here is that aggregators are bonded. And if they put an invalid transaction into a block that's bad, they're going to get slashed. So they're not going to do that. Provided the bond is sufficiently high, the risks for the average user is basically 0. And everything works as we want. We have near instant transactions, we have state channels, we have smart contracts, and we have no gas except for the aggregator fees. And because anyone can do this, as long as they're bonded, you could even produce a marketplace for aggregators, much like the same way you have miners competing for regular block production on your mainnet. This is great. This is like the holy grail of this, and didn't actually need to be complicated, right? The Plasma exit games, we don't even talk about them yet. All we need is a fraud proof. Basically, if you can simulate a state update, and if you can simulate that going wrong in some cases when it should go wrong, like someone submits something false, if you can catch that, that's all you need for the system to work at this point. We've made massive gains by distilling all the essence. Question.
Yeah, are there front-running issues with the previous scheme?
Front-running in terms of the aggregator, like who's aggregating?
Yeah, since anyone can submit, can't anyone front-run as well?
I think you could have slight issues with that, but it doesn't affect the overall security of the system too much. It should be just like mining, where you'll have different. Okay, so yes, you can front run the transaction, but if you have signed transactions, you shouldn't be able to copy transactions within that block, unless it's public. Just like it should mimic exactly the Ethereum mainnet block production issues.
Okay.
I don't know if that answer is that clear.
Well, in the Ethereum chain, you get like uncle chains and all that stuff. So I'm just wondering how the
yeah, so here it's even simpler than that. You have no forking. You can't have forking because literally the first person puts in a block, and it had better be a direct update from the previous one, or at least a compatible update, or it will be rejected. So you never have forking in your sidechain for Optimistic Rollup.
Okay, cool.
Whether or not I made that clear is another story, but forking disappears. You no longer have Uncle Block. And this is a bit of a subtlety based on the fact that it's first come, first serve, and on the mainnet. Which also makes it sort of, it sort of incentivizes honesty even more, because how are you going to make that really hard? Like, it seems harder to me to make a bad block when you don't know who's going to win the block between, the one you just read and the one you're producing. But yes, it's more.
So this shadow chain supports current tooling, but potentially, and it supports smart contract execution.
Mm-hmm.
Is it supporting like most current form, like most current updates on that? Like I guess do current problems with smart contract development, would that still then be seen in these rollups? It doesn't really change any of that. It just is another way to sort of increase overall state execution and transaction speed and throughput.
So I'm going to say that more or less anything you can do on Ethereum will, like deploy on a mainnet, will be more or less deployable on an Optimistic Rollup chain, at least the one produced by Optimism using this OVM, which we haven't talked about the OVM in great detail. But there's a bit of a caveat. The caveat is some things have to change, right? Where do you deploy your smart contracts, and how does it affect the contract actually? So I think technically the full suite of Solidity opcodes are available to you. And so technically, everything should be more or less the same. In reality, because you're not necessarily deploying your smart contracts on the mainnet, you're deploying them on your rollup chain, there might be nuanced things that you need to take care of. And I'm not saying there's an explicit list of security considerations I have yet, but if we get a contract that is designed for rollup deployment rather than mainnet deployment, we should think more carefully about what that means. So
got it. That answers my question.
It will come clear
explicitly.
because we haven't talked about using the OVM yet, and if it was exactly the same as the EVM, I wouldn't need to talk about using the OVM. Right? So there's clearly something different, but let's talk about this. But first, let's see what happens. Okay, so optimistic rollup. How do we get here? Well, we go from ZK Rollups to here by basically saying, okay, instead of proving every time everything is always correct, we're going to say assume it's correct unless someone proves you wrong, right? And so again, if you're only concerned about your money, just watch your state transitions. Something goes wrong, you can generate a fraud proof, and then you will take the bond of the aggregator, and you will possibly even make more money than if things have gone right? Sort of good news for you. Unless you don't want to do it, in which case you just stress the system, and maybe someone else will cache it because everyone else can still get that same bond. We have constant size updates. Again, you're only publishing headers. You probably want to publish the data. Maybe that's not constant size updates there. But I guess you bound the block size that's also constant. So that's probably where that comes from. You get gas savings, which are enormous because now you're not doing any smart contract execution except for these updates. Again, all you're doing is publishing these headers and this constant sign up updates. And if you have a smart contract on your rollup chain, has maybe a different notion of what gas costs. Maybe it has no gas. Depends what your rollup chain fees look like, and what those system constraints. And in principle, anyone can be an aggregator because, why not? You put up a sizable bond. You say, I'm going to take some transactions from this system. Now, of course, I'm sweeping a lot under the rug, right? If it's sort of a private rollup chain where you need to submit transactions to like a login website, obviously not everyone will be privy to the transactions you can put into a block. But for the open rollups that will exist, or at least I hope will exist, anyone can do this. And so this will be just another way to also put your computer to work if it's really sitting idle and your hydro bill is too low. And basically you collect these the same way as we did before. You typically collect them on the second layer or layer 1.5 or whatever layer this is considered, and then that translates into some value for you on layer 1 through a withdrawal mechanism of some kind. Challenging, pretty straightforward. I'm running out of time again. Basically, we just verified all the sane stuff, right? Transaction inclusion and order better be there. You have nonces to guard against this. This is fine. Verify that you're storing it literally in the right storage spot. The Merkle state needs to be constructed in a careful manner. I don't want to go into details that much. It's not even that careful. Just some indices for some places, all that. And then just check the result. And if it doesn't work, okay, you're bad. So how do you actually check that last step? Step 4 is the hard one. Well, step 4 is the introduction of the UVM or OVM, which is the Optimistic Ethereum Virtual Machine. Basically, this is implemented in the rollup contract on the mainnet, and opcodes that change state basically now just change, now call functions on the mainnet. So basically, when we do storage updates, in addition to publishing this header, right, I said we'd be tracking data, but that's still constant because your block size is constant. There's all that. You have your state being stored on chain, on the mainnet somewhere, right? And so if your smart contract on your rollup chain calls store and all the state's supposed to be stored on the Ethereum mainnet, there has to be some work that connects the storage of that smart contract on the rollup to the mainnet storage. And so now what you do is you transpile these contracts into a function call instead of that opcode, and you use the OVM, whatever, to check that this is correct. And so but it's also compatible in the sense that it works allegedly 80% of tooling. So I think something like, all of your truffle config can be set up to run an UVM instances instead of some sort of EVM instance. I don't know if it's replacing Ganache explicitly or some other version, but the tooling is supposed to work more or less the same, except for that possibly 20%, which they didn't describe, which is nice. UVM basically consists of is three things: transpiler, a safety checker, and execution manager. The transpiler will take your code that you want to deploy on a rollup chain and say, okay, it's store. Now you're calling a function called store on some contract here, which guards your data. A safety checker that literally just says, oh, you didn't try to write an opcode that doesn't exist in Ethereum. Right? We only support these opcodes. No new opcodes, please. It's pretty straightforward. That probably doesn't take too much to look at. And then 3, which is just tries to actually execute things for you and sees if the state would update exactly the way it was supposed to. So more concretely, let's look at an actual example of sort of what could go wrong. Right? So if you deploy a contract like this one on block 2 on your rollup chain, right? You might have a function that says do bad stuff, right? And if the timestamp is greater than 5, right? Say it passed 5 seconds from now, do something, otherwise you're not going to do anything, right? And because this is being executed on a rollup chain rather than a Ethereum mainnet chain, right? The Ethereum block timestamp might not correspond one-to-one with your rollup chain. And so your rollup chain needs to sort of handle this in a way that's meaningful. And I think this will actually cause a few hiccups for developers in the future. They allege that this is not problematic because of the transpiler, but I don't know that they've really thought every corner case out yet. Right? Because, for example, if your rollup chain is executing this contract at block timestamp 2, right, the bottom branch does nothing, it will execute. But if you haven't updated a rollup branch or a rollup block in quite some time, then you'd execute it on real mainnet timestamp 8, something bad could happen, then that would be, a situation where your smart contract needs to be concerned. And so what you do is you transpile. And so instead of saying exactly what the block timestamp is, so on the Ethereum mainnet, you sort of just map it to number of blocks from the rollup timestamp, right? You can just switch the context of what that function call means. And you do that with a transpiled call. Instead of calling block.timestamp on the Ethereum mainnet, you have a different counter. And so maybe the slash should also come earlier. If you have an original code for the transpilation that has an S store, basically you just transpile it into a function call that, there's some function in the rollup smart contract main chain, on the smart contract for the rollup on the main chain, that says, function custom S store or something, where it takes as parameters the smart contract address of the deployed rollup contract and the data it wants to store, and it updates the data on chain in a way that's meaningful. This does incur some gas overhead because it's not the same as just storing data. You have to store data in a well sort of indexed way. But they allege it's only 20%-ish more. And for opcodes that don't change state, it's 0 overhead, because addition is addition no matter what blockchain you're on. Right? As long as you have the data and it doesn't change state, it's free. So this transpilation might be a security concern in the future. I sort of expect there will be someone who screws this up, but let's see if this takes off. Optimism works. I already talked about what these are. Optimism works, this is what I'm trying to say, to some degree. Instead of doing the OVM, the UVM, or this transpilation, they hard-coded certain opcodes, and they basically made a layer 2 Uniswap. I think they literally forked Uniswap and put it on a rollup sidechain and say, hey, look, it works. And now you have instant Uniswap on layer 2. And you can go to this and you can use it. You can play with it. As I expected, I am out of time. It's uniswap.exchange, I believe. Go see what it looks like. If it's instant, that's because it's on rollups. Great. If you find something wrong with it, claim a bond. I don't know who the aggregators are, but hopefully they're bonded. So now we've talked about everything. One thing I guess I glossed over is you can still recompute all your state because all the store operations map to some function on your Ethereum mainnet, right? In principle, if you're concerned about your state being out of sync, go replay all the Ethereum blocks, collect that data yourself. Obviously that's automatable, but it's, it might be annoying, but you don't have to do it, and you can do it, which is strictly better than the Plasma version. And it allows arbitrarily many people, which is strictly better than the state channel version. And it's much more simpler and supports greater features than Plasma. So I think optimistic rollups are probably going to be here to stay until someone does something better. If you are interested in learning more or contributing, these are good places to start. Interstate Network, they're working on some. Fuel Labs and Nutberry also. IDEX has some interest, but I couldn't find any code. Take that with a grain of salt. And I believe some people at Princeton are actually looking at this in some sort of academic setting, but I didn't read that paper in full. So that was a lightning talk of rollups. Hopefully you have some idea of what they are. If you don't, please ask your questions now or any other time. And if you want a full list of reading materials, I can publish whatever folder I made on Chrome. Thanks.
Hey, is anybody currently using this, or is it just like on a research state?
So it's much more like Uniswap Layer 2 seems to exist. I don't know to what extent that has seen traction. But there are projects.
Uniswap, I think they only did like a proof of concept.
Yeah. So you're right.
Transactions.
It probably doesn't have like all the liquidity pools and stuff anyways. It probably wouldn't be. I don't think anyone's using it in earnest. I think people want to use it. And I think there are people who don't know they want to use it that want to use it. But all of the projects that I listed there are yet to be deployed in a V1 sense. So there might be prototypes on testnets, but no. So no.
Okay, thank you.
Any other questions?
I have one. Are there multiple? Is it possible to have multiple roll-up contracts? So there's an infinitely many number of these sidechains.
Yep. Yeah, and because assuming that Transpiler does its job correctly, you can nest them as well. So you can have vertical and horizontal scaling.
And assuming that like the same user would, let's say, have a balance on the mainnet of whatever 10 Ether, and they would go on independent roll-up sidechains and spend some Ether, maybe like at the same time. How much time would it require to detect this on the mainnet?
So obviously you have like the rollups probably won't let you spend until they're confirmed. So it'll probably take 6 transactions to get your money into a rollup chain. But once you're inside the rollup chain ecosystem, it's as quick as there are people sort of running these validators, this UVM type system. Or if there's basic transitions, maybe you don't even need that heavyweight tool. But it's as quick as it would be to just check every block that gets produced. So in principle, miners for Ethereum do this. I know in practice they probably don't, but it's as quick as it needs, or it's as slow as replaying all the data changes that you care about.
But wouldn't all the updates that need to be done from those blocks on the side chain, if they were transpiled, would they fit into one block on the mainnet, or would it be maybe necessary to split it into multiple blocks on the mainnet? Because in the figure that you had on one of the slides before, you had like each of the blocks on the side chain were mapping to one block on the main chain.
I don't know the size of the roll-up blocks. It's possible you might need one real block per roll-up block, in which case there might incur some additional slowdowns as well. But I guess that's still not worse than if confirmations. So on the other hand, if you can fit multiple blocks into a single Ethereum block, this problem gets better. I don't know that it's solved. I don't know. Yeah. I guess you can.
Okay. Thanks.
Yeah, somewhere I got this note that says it's constant size. I don't remember what that size is. So that will get the answer. Any other questions?
Can you talk a bit more about the transpiler?
Sure.
So what is it actually doing? is it just basically taking the opcodes from the rollup chain and writing that onto the Ethereum main chain?
So basically what happens is you have on the Ethereum mainnet a contract that has a corresponding version of each one of these opcodes that affects the state of the contract. And the transpiler takes the contract that you're going to send to the rollup chain on the other side, and it strips that contract of all of those opcodes, because you're not really trying to store anything on the side chain. You're only ever trying to store it on the main chain. And every time there should have been an opcode that says affect state in some lasting way, they replace it with a function call to the contract that contains the mapped version of that opcode. So instead of calling, a store, I call a function custom store on contract wherever it is, which is either hard coded or passed in to the transpiler. And so that every time the contract were to update writing something, it would get the right position to update it on the real mainnet as appropriate.
Oh, got it.
Right, and similarly for reading, in particular, if you're, I think in this example, which not my slide, if you're trying to read the block number, for example, right, if you left that opcode in and maybe your Ubium wasn't configured right, maybe you'd read the mainnet block number when you wanted to only care about the local context, which is the rollup block number, right? And so there are sort of some interactions that need to be much more localized, and yet you still want full availability on the mainnet, which is why you need some map function to sort of deal with these things.
If you because the rollup chain is faster, right? So if you want to get something from the mainnet, would it lock up your contract?
No, because you can read from the mainnet easily, and then even if you process a bunch of states, so say you can produce rollup blockchains every second, but a Ethereum block takes 10 seconds, right? You'd like to ideally be able to produce 10 state updates to your data in the same time that the Ethereum block takes to produce. And you can actually do that because what happens is for every one of these state transitions, you just sequence them, you put them in sequence. And so your aggregator will just take them in sequence. If they all fit into one block, that's fine. And if they try to take the last 7 before the first 3, for example, and they're not compatible with what the main state looks like, then they'll get slashed if someone catches them. So because you have nonces still, essentially is.
Okay, so if, like, for example, let's say like my rollup is processing transactions every second, and then the main chain is every 10 seconds. And I have like transactions that basically say like add 1, -1, add 1, -1, add 1, -1. Then I guess the aggregator would add all that up to 0.
Yeah. So it'll either take all the transactions and state updates and put that into one state update, or it'll just try to submit 10 different state updates. But as long as they go into one, or as long as they go into the appropriate amount of roll-up blocks, it doesn't matter what they do. And
is there any like transaction order dependence type of thing? Like,
I mean, there could be, because your smart contracts on the rollup chain could have transaction order dependencies. But if you send from an account, your account, if your rollup chain operator is smart or is configured in such a nice way, let's put it that way, then the account should also have a nonce. In which case, the nonces guard against bad ordering. So within smart contracts, I'll say definitely yes. Outside of smart contracts, I would say not if they were smart about making the rollup.
Oh, you need the rollup nonce.
Yeah, because basically you'll have 2 accounts. You'll have 2 account nonces. You'll have your main chain nonce and you'll have your roll nonce. or at least that's how I would implement this. And I didn't check that detail, but if they didn't have a rollup nonce, that would seem problematic to me. Very much so.
Got it. Have they built the transpiler yet, or is it still just?
I don't think so. There's an UVM for download somewhere, but I don't. I have to get back to you on that. I can't remember if I saw that download link and I just ignored it, or if it's coming. I'll get back to you.
Got it. Okay, got it.
Any other questions? Okay, well, let me know offline then if you do.
Jan, actually, I have one last question. Could you consider that the OVM is almost in a weird way like a virtualized, I mean, it's not, but could it almost be comparable to a virtualized EVM running in the EVM?
Yeah, that's sort of the goal, right? You want to be able to somehow verify real EVM transactions using your sort of existing EVM as a guard.
Okay, that's great for yay immutability. Awesome, thank you.
This was awesome. Thank you.
Thanks, Jan.
Thanks.
Thank you.